People outside can come in. Okay, everyone's inside. Let's start. So welcome back to the post-lunch session. And the first talk we have is from Lei Yang, who's doing Mega ETH. Very happy to have worked with Lei on several projects as a collaborator. And he's presenting SALT, breaking the I/O bottleneck for blockchains.
All right. I'm very happy to be here and really honored to join this workshop. It's and thanks a lot for David for inviting me and for people who are organizing this this workshop. And I'll talk about this work that is actually, unfortunately, not related to consensus that we're doing at Mega ETH on unblocking blockchains from the I/O bottleneck coming from this authenticated key value storages. And this is a mouthful of a title, so based on my learning from David, the shorter the title is, the more interesting the work appears. So I'll just call it Small Authentication, Large Try. It's actually the name of the data structure. It's called SALT. So I'll just, given the expertise of the audience, I'll just spend maybe 10 seconds going through this slide. It just talks about what is an authenticated key value storage, right? It's just a Merkle tree. And yeah, it's really frustrating that there are many different names of this primitive. Someone calls it AKVS, someone calls it authenticated databases, someone calls it authenticated dictionaries, but we're gonna just stick with an AKVS in this talk. So what's nice about AKVS is that you have this commitment which you can use for, say, state settlements from layer 2s to layer 1s, light clients if people are still interested in this kind of stuff, and all sorts of interesting stuff, like for example, cross-chain transfers, right? You need to prove that something has happened or some state is true as of some block in chain 1 to chain B, so that you can, say, move money between the chains. But what's really sad is that maintaining those state commitments or updating those AKVSs when you update the underlying state is actually pretty costly. So what you're looking at here is a bunch of benchmarks we did. On the x-axis, we vary the amount of memory available to a Rust Ethereum execution client when it's running through, I think, 100K Ethereum blocks, mainnet blocks. And on the y-axis, you're seeing a breakdown of the time it spends executing those blocks. So it's pretty unfortunate that across the board, you are seeing that updating this AKVS taking almost 5.8 times to almost 10 times longer than just running through the transaction. So it's pretty funny, right? You spend, say, 1 second executing transactions, computing everyone's balance. You spend 10 seconds updating the Merkle tree. And it's killing the performance of execution client. And that's kind of the motivation of this talk. And the reason that we know that Merkle producer tries are the data structures that Ethereum uses as AKVS. So the reason that they are really slow to update is because we know in MPT data structure, each node is the hash of its children. And when you update a particular key, the thing you do is that each path in this Merkle Patricia trie also represents like a snippet, like a segment of the key, right? So you chase the correct edges until you find the key that you're looking for example, 8 bad food, right? And then when you update the value, the key value pair, you have to really trace it back to the root to update all the nodes that you have touched. And it's these random disk IOs, because these nodes, they all sit somewhere on the disk. You actually cannot predict the path that you're going to access. So it's those random disk IOs that kill throughput. It's actually killing throughput, not just latency, because modern SSDs, they are much, much more efficient when you give it like a very regular serial work to work with instead of just throwing random probes here and there, right? And on the other hand, MPTs are actually kind of nice. They have some very interesting properties. One of them is they are history independent in the sense that the shape, the like internal construction of the MPTs only depend on the currently stored key value pairs, not the history through which those key value pairs end up being there, right? It's not dependent on the insertion deletion history. It's only about the current thing that you're storing. It's a very nice function of what you're storing here. So what it enables first, it enables straightforward and succinct non-membership proofs. Non-membership proof basically says that you want to prove that something does not exist in the AKVS. And also, it's very easy to reconstruct in the case that the AKVS is lost, or in case that you are like synchronizing with a node. It's very easy to reconstruct the AKVS because you only need to get the leaves. You only need to get the key value pairs. You can do whatever you want locally instead of having to follow the history through which the data structure is constructed, right? And also, it's a pretty subjective matter, but having the data structure being a function of the content it stores is a pretty elegant feature. And also, by the way, MPTs, they also have very, very modest resource consumptions because it's just computing a bunch of hashes. So our wish list, sorry. Yeah, of course.
With regard to the previous slide, is this copy on right, or are you updating in place?
We are updating them in place. But same goes for copy on write, which can be even more random, the workload.
But the write workload would then not be random.
Yeah, exactly. The write would not be random, but then afterwards the read will be random. Yeah, so either way, yes. Thanks for the question. So our wish list, okay, so we want to preserve the two nice properties of MPTs, and we also want to minimize disk I/O, which is what's killing us for performance. So a crazy idea here is, what if we just throw the entire AKVS? Of course, we're not crazy enough to also say that we want to throw the actual key value pairs into the system, into the memory. But what if we can just fit the entire trie, the upper side of the trie, like the authenticators, to the memory? So then it's basically incurring 0 disk IOs. It's like cheating, but it's also pretty practical. So in order to judge if we can actually do that, the very interesting metric we have to look here is what we can call storage overhead or storage efficiency, right? It's the size of the trie, not including the actual key value pairs, divided by the number of key value pairs that you want to authenticate to, right? It's basically the per key cost for it to be committed to, right? So again, let's look at MPT. In MPT, we use a radix of 16. Here, radix parameter R tells you how many children, at most, a node can have. Suppose that there are n key value pairs, then in the ideal case, because we know that a node can have at most 16 children or R children. So one layer above the leaves, or one layer above the key value pairs, you are looking at at the minimum n over R nodes. And it goes on to the root. So if you add this series together, you are at n over R minus 1 in total. And that translates to 2.13 bytes per key. And we are assuming 32-byte SHA-256 hashes. And that's about 3.2 gigabytes for 1.5 billion keys, which is kind of a recent metric, a recent measurement of the Ethereum blockchain. So it looks pretty nice, right? But however, it's a pretty unrealistic assumption. And especially the unrealistic assumption is that we're assuming that every node, every internal node of the trie is having all of its potential 16 children filled up. We're basically assuming a complete regular tree, which is the dream of computer scientists, but it usually rarely happens in the real world. And the reason that it does not really happen in the real world is about key sparsity. It's about like the sparsity, especially down here. And it's because, remember that there is some meaning about the path through which you trace from the root to a particular node, right? For example, here, this node, the entire subtree of this node share the same prefix of the key, which is 0xDAD. And here, if you go one step further to this node, then it's actually DAD B, right? So the deeper you go, the longer the prefix, the longer the shared prefix you are assuming. And you only have so many keys in your system. So if you go deeper and deeper, the number of children or the suitable keys you can find for a node is becoming fewer and fewer. And at some point, it will just stop fitting filling up all of its 16 possible children. So that's the logic flow. Basically, the deeper the node goes, the fewer keys it has, and the more underutilized it is. And the underutilization basically means that we have to find other keys we have to find other nodes to provide for the capacities which it's not providing, right? And here is some analysis. So we have some experiments showing that this analysis is kind of correct. We're kind of approximating a non-memoryless process and use a memoryless process. So it's at small, relatively small arity. It's not that accurate, but it's fine. So here, the blue curve is the real radix trie, 16 array, and it's basically taking about 16.8 gigabytes for the same 1.5 billion keys workload that was mentioned. So it's several times higher than the ideal case, right? So it's just one example. So currently, so as of now, we know that, okay, so we really need to reduce the size of the trie because 6.8 gigabytes, not even including any other metadata that you need to store, is not really realistic for, say, a low-end laptop to run an Ethereum client. So we need to keep shrinking the size of the tree. And one idea is that what if we just increase the arity of the tree? Because as you increase the arity of a tree, it flattens the tree and also it reduces the number of nodes. So would we just do that? And it's actually considered by, say, Merkle tries, which Ethereum considered to be a replacement of Merkle Patricia. I think the plan is scrapped, but I think they were considering R equal to 256. Radix, and or there are databases that are optimized for Merkle Patricia tries that are trying to pack a small subtree into a 4 kilobyte page on a modern SSD, just to like make use of the unused I/O bandwidth. So, but unfortunately, these methods also don't work because as you increase the arity, it also increases sparsity, so it kind of cancels the effect. And this is one example. If you use 256 array, yeah, it works better, but still much worse than the theoretical optimum, which is complete trees. And actually, you can also do some theoretical analysis, and you can see that even if you keep increasing arity, at some point it saturates, which is actually quite interesting. The purple curve is the average overhead, averaged over trie sizes, and the shaded area is the worst and the best storage efficiency. And you can see that the best is kind of decreasing, but it's not decreasing as fast as the optimal case, and the worst and the average cases just stay here. And this is like a same figure zoomed out, so it's really converging here. Okay, so quick recap, we want to minimize disk I/O, and our crazy idea is to fit the entire authenticated, the entire authentication data structure in memory. But the problem is we want to really minimize the size of the tree so that we can fit as many key value pairs as possible given a finite amount of memory, right? And we saw the challenge, which is that radix tries, which are, say, MPTs or Merkle tries, they are sparse, especially towards the bottom, and they are inefficient. They are storage inefficient. So an insight here is that actually, even though the entire tree, when you look at it as a whole, it's inefficient because of sparsity, not the entire tree. It's actually not like it's not homogeneous across the board, right? What you can do is to like break down a normal radix trie by levels. So for example, here I'm showing in blue shaded area the first 4 levels of the trie, and the orange area the remaining levels. And after a certain point, the first 4 levels are actually filled up. You can see that the contribution of the blue part dies down. It only makes sense, right? You cannot fit an infinite number of key value pairs within a finite number of levels. So the insight here is that if you are willing to just use the trie for some certain number of, at least some certain number of key value pairs, the first few levels becomes very efficient. They are kind of converged to complete trees. So that's kind of the insight that we're taking here. And that basically says that an optimal data structure should be heterogeneous in the sense that the first few layers, they are going to be complete anyway. even if you just do a normal radix try. So you just take it and just do a static complete tree. Just force it to be a complete tree, right? Just because you're not really wasting too much space. It's almost complete. It's almost guaranteed to be complete. On the other hand, the bottom layers, as we saw, they are pretty sparse. And when they are sparse, you cannot really afford to construct indexes over those sparse trees anymore because you are just throwing a lot of internal nodes for just a few key value pairs. So what you should do is to flatten them, flatten each subtree into a flat open addressed vector or hash tables, depending on how you want to provide random access into those buckets. So again, you want a static main try, which is almost guaranteed to be complete, so you don't really lose that much efficiency here, and a series of dynamic buckets that can deal with the sparsity of the key space. So this is kind of the main idea of sort. In sort, there is a main try, as I mentioned. It's D levels, D is a parameter of complete R array tree. And here, each node in this tree is the vector commitment of its children, right? And the nice thing about being a complete tree is that it can be packed into an array. So no need to store pointers, so it minimizes the space cost. It's very easy to implement. The code is very clean, and also its parallel updates to this try is very easy. I'll skip what is vector commitment. And OK, so below the main tries, you have buckets. Each leaf of the main try corresponds to one bucket. So here, basically, we have R to the power of D minus 1 buckets, because there are R to the power of D minus 1 leaf nodes of the main try. And each bucket is a vector, but the way you manage the vector, because you also want some pretty efficient random accessing to it, you manage it as a strongly history-independent hash table. And the fact is it's flat, as I mentioned, it's always space efficient. It's just one vector commitment over the entire content of the bucket. No intermediate nodes to deal with. Always just one vector commitment. Always the same constant storage overhead. And the SHI property makes sure that the entire data structure is also history independent, which is what we want. So I'll walk you through the insertion process. First, we find the bucket, and it's exactly what you would expect. You first hash the key of your entry into something hopefully uniform, and you take a mod over R to the power of D minus 1, which is the number of buckets, right? And that's the bucket you should be looking at. And then you just perform your normal insertion process into this SHI table. And after you insert, you will find that your key is inserted into some particular index into this vector, and that's your so-called bucket slot. And a sort key basically uniquely identifies a particular position in this data structure. Is like a combination of the bucket ID and the bucket slot. And then, of course, you have to propagate back the vector commitments all the way up to the to the root, and we use we use inner product arguments for vector commitments. Okay, so there's actually something interesting that you also can do with this data structure, which is decouple authentication and storage. And this is what it is, right? So the observation here is that we've mentioned that we want to use SHI tables to manage those buckets, but actually, they only need to exist in your imagination, right? It just defines, given a bunch of key value pairs that you have inserted that exists in this vector, what's the representation? What's the arrangement of those key value pairs when you want to compute the vector commitment? It's just for dictating how you should compute the vector commitments over a bunch of key value pairs. This is not about dictating the physical layout of the key value pair. So what you can do is you can just throw in whatever, say RocksDB, LevelDB, any key value storage, and store the mapping from sort key to actual key value pairs, and that's it. So of course, this key value storage exists on the disk. The overhead is really small. in addition to the key value pairs, it's only 4 bytes of extra data for the sort key, for the key to the key value storage. And of course, the main trie, as we designed, we want to fit it in the main memory. So it's r to the power of d minus 1. Leaves is actually not r to the power of d minus 1. It's a series. But on that order, times 64 bytes per node. We're using IPA. And that's it. So the bucket exists in your imagination. Does not really need to exist physically. So there are some caveats. One is that if you modify, it's always in place. But if you insert or delete into the SHI table, of course, you sometimes have to move around existing items just to keep the SHI invariant. So sometimes you have to move around extra keys. But turns out that the constants is not an issue in practice. And also, what if you run out of space? It's fine. You can just add more segments, and you can also compute. You can also construct a tiny complete trie just for a particular bucket, because now it consists of multiple segments, right? It's easy. And membership proof, you just do a SHI table lookup and open the vector commitments. And non-membership proof, you also do an SHI table lookup. But it's basically what happens when you want to probe into a key that does not exist in your hash table, right? You basically what you do is search until you find an empty slot. So you kind of open all the slots that you've hit, including the first empty slot you have hit in a failed search in a hash table. And you open all of those in vector commitments. OK, so some analysis. We use R equal to 256, D equal to 4, and 64 byte vector commitments. And the main trie is about 16 million nodes. And that's about 1 gigabyte of memory footprint. And each bucket initially was also set at 256 slots. So all in all, it authenticates to about 4.3 billion key value pairs, which is about 3 times the size of a current day Ethereum blockchain, and that translates to about 0.25 byte per key value pair authenticated to. And the overhead stays below 0.5 byte per key, even if you start expanding those buckets, and it eventually converges to 0.25. And this is the comparison with all the schemes we have talked about, and you can see that sort actually converges very closely to the theoretical optimum, because OK, so I/O cost always 0, and in terms of the main trie, which sits in the memory, to the buckets, of course, you have to update the underlying key value storage, but it's something that you have to do when you execute blockchain transactions anyway. It's totally separated from the authentication data structure. And as I mentioned, during insertion deletion, probably more, but turns out that when the load factor of the SHI tables are not crazy, it's not too much. Computation cost, we're using vector commitments, so it's definitely much more expensive than just computing hashes, about 20 times more expensive than Keychack 256. But we did some experiments. What's nice is that it's actually pretty parallelizable. So at 1 core, you can do 45,000 keys per second. Again, it's totally compute bound, right? There's no I/O happening. It's only about computing those IPA updates. And we're using a desktop CPU. It's about $500. So finally, some comparisons with other state-of-the-art constructions. First, NOMT, near optimal Merkle trie. It's basically a binary Merkle trie, but with nodes packed into 4 KB pages for fitness on more than SSDs. And also QMDB, it's basically packing a journal, basically the updates and deletions to your key value storage into a Merkle mountain range with garbage collection. And we're assuming that we're running the hybrid mode, which uses about the same amount of memory as SOT and NOMT. So benchmark numbers, SOT can do about 87K updates per second. I know it's different from the number I showed before. We did some updates. It's from a new experiment, new code. And QMDB about 63K, and NOMT about 40K. Disk space amplification, very small for SOT. NOMT, we're not sure. We didn't run experiments. QMDB, because it's garbage collected, it's basically a trade-off between amplification and your I/O. Computation overhead, definitely the highest, but it's manageable, and also it's very parallelizable. You can even use GPU. And random disk IOs. So yeah, that's it. We talked about Salt. It's a new authenticated key value storage that scales to tens of billions of items while completely eliminating random disk IOs while being very space efficient so that you can fit the entire thing in the memory, which is the purpose. The key insight is that tries or radix tries are sparse at the bottom, so you want to flatten them into proper vectors and just use one authenticator for them. Optimal space efficiency for the in-memory stuff, it converges to complete trees, so it's pretty optimal. And the on-disk key value storage, we call it optimal because you can just use the state-of-the-art solution. We don't really dictate anything, right? You have all the flexibility. Reasonable computation cost, and it's been running live since day one of Mega ETH testnet, which we launched earlier this year in March. And yeah, feel free to check it out. Thanks. I'm ready to take questions.
You have a very nice slide where you compare the time it takes for computing the commitment versus for execution and other things.
Oh yeah.
And do you have a similar slide with Salt? Just because that was very good to understand the latency
yes.
overheads.
So Salt, I don't have the. It's
this one, yeah.
Yeah, exactly. It's very labor intensive to run this experiment. So we didn't, but we have a qualitative answer, which is once we move to Salt, disk I/O is. We also test the disk I/O like bottleneck, but it's 3 times higher than what the EVM execution bottleneck is. So we have like a 3x runway before we run into disk I/O issue again. But then, even then, it's going to be key value storage access when you run those transactions, not when you are updating those commitments.
So you're not gonna hit this on the update.
At least for update commitment, it's fully disentangled from I/O, and it's all about computation now. So you just throw in more CPU cores.
Okay, thank you.
Yeah.
Is there code available?
Very soon. We hope to get to mainnet. Fingers crossed. Yeah.
But the testnet code isn't available.
It's not available yet, but we are actually preparing for audit, so it's shaping up. Yeah, it'll be available. Yeah.
Can I connect?
Yeah, of course.
Does it work for adversarial updates and key access?
Very good question. Yes. So there are at least two types of attacks. One is you try to increase the size of a particular bucket too much, and for that we just rely on economic incentives. So we assume that as you expand the bucket, at least once you start to increase the insertion cost into that bucket. Yeah. And the other type is you can create pathological cases in particular hash tables, but that you can just use rehashes. You can add a nonce here, and once you're unhappy about the state of the hash table, you rehash it, you shuffle it. Yeah. Dalia.
Maybe in the interest of time, we can take questions.
Of course.
Thank you very much, Lei. And the next talk is Autobahn, presented by Professor Natacha Crooks from UC Berkeley.
Thank you. So this morning it was the Berkeley coffee that didn't arrive, and now it's the Berkeley laptop that can't connect to the Berkeley projector, so I concede Stanford wins. But with that, so very excited to be here, and very excited to tell you about our project, Autobahn, which is a new Byzantine fault-tolerant consensus protocol that we published at SOSP last fall, and that we've seen some sort of recent adoption in industry. Now, for those of you who don't know, Autobahn is the German word for highway. So the German highway famously has no speed limit. So when you think of Autobahn, I'd encourage you to think of a Ferrari going 200 miles per hour on the German highway and not on the Berkeley-Stanford congestion stretch. So with that, at a high level, Autobahn really strives to do 2 things. The first is that we aim to build a system that accounts for more realistic network conditions. So something that offers high performance, both when the network is behaving well, behaves gracefully, but also when it recovers from intermittent turbulence. And what we found is that networks tend to not be super well behaved in general. They're often quite blippy. The second is that we'll obviously make the case that thinking about BFT consensus doesn't need to be a dark art, and I'm sure you all agree with that, and that it can be simple. And that's paramount for building systems in production. Now, what I find funny about introducing this line is that the next 3 talks are also going to claim to have a protocol that is simple. So I'm going to say this is simple for my definition of simple. So let me, before we get started, let me briefly set the stage. So I don't think BFT needs a huge amount of motivation for this audience. So very quickly, just to clarify what I'm talking about, BFT consensus is at the heart of the blockchain stack and promises to implement the abstraction of a shared, totally ordered ledger, meaning that every participant orders the same set of operations and does so in the same order. And these guarantees hold even if a subset of participants misbehave. Here we're talking about n participants and f possibly arbitrary faulty nodes. Nothing special here. So BFT consensus has a hard job. It's a really nice abstraction to have, but you need to implement it well. And for it to be useful, it needs to have high throughput, it needs to have low latency, and obviously, as the name suggests, it needs to actually tolerate Byzantine faults. Namely, it needs to be robust to arbitrary network failures. And you have to do this while dealing with the troubling reality that our networking colleagues haven't yet figured out how to make the network synchronous. And famously, consensus is impossible in an asynchronous network. But obviously, that would make for a very short talk. So what do we do? Well, to deal with this, practical solutions that are deployed today look to partial synchrony. So in this model, we basically use timeouts to approximate synchronous intervals and try to detect faults. So we're going to maintain safety at all times, but we're only going to offer liveness when synchrony eventually holds. And in BFT theory, this is typically modeled as something called the global stabilization time, or GST. And this is basically the period after which timeouts start holding. And now this model allows us to rigorously talk about what a protocol does, but obviously there's a big gap between the bookish version, where there is a point at which GST will hold forever, and what we deployed in practice. And current systems have to deal with the practical reality today. So in practice, this rosy reality of ever holding synchrony is of course a fiction. And, current protocols recognize that. Missed timeouts are common and can trigger for huge kind of behaviors, ranging from DDoS to network delays to simple replica failure. Now, the cause of those events doesn't necessarily matter for our use case, so I'm going to bundle them under the umbrella of something called a blip. Now, a blip is anything that temporarily interrupts the progress of consensus and requires us to take action to recover. Now, something that I want to emphasize here is that these blips aren't fringe cases. Instead, as the name partial synchrony suggests, blips are the common case because synchrony is truly partial or periodic. And this means that to claim good performance, a partially synchronous system needs to perform well both in the absence of blips as well as during their resolution. And this is really the problem that we're going to target today. So existing systems don't handle this disconnect super well. So if we take a simple experiment with Hotsoft, one of the most popular BFT protocols today, we're going to simulate a blip caused by a single replica failure. And we're going to run the experiment with this fixed input rate close to the system peak throughput. And the graph is going to show latency relative to its start time. So, latency of transaction commit relative to its start time. So during the blip, Hotsoft is going to make no progress, and as a result, the incoming requests are going to form a backlog. Once the blip resolves and the progress resumes, this backlog needs to be worked off. But you can only do so, you can only work off this backlog as much as the excess resource capacity allows you to do so. And this is going to result into a performance degradation that is actually going to last well beyond the resolution of the initial blip. And we're going to call this problem a hangover. This is the effect of trying to recover from a blip. Now, I think everyone's going to agree that hangovers, whether it's in real life or in consensus protocols, are undesirable and we want to avoid them. And ideally, we'd like to tolerate a blip very much like this. During the blip, we're going to continue to lose progress. That means that transaction latency is going to increase. But once the blip ends, we're going to immediately make up for all lost throughput and return latency to normal. Now, we're going to call protocols that achieve this property seamless. A seamless partially synchronous protocol should fully avoid hangovers, and perhaps obviously it should do so without cheating and simply killing liveness altogether. So in particular, we're going to want to develop seamless protocols that do not produce more blips in the process, because otherwise that defeats the point. So on that note, let me introduce Autobahn, which promises to satisfy all the sort of tough demands that we expect from BFT, as well as seamlessness. Autobahn wants to achieve high throughput, low end-to-end latency, and seamless recovery from blips. And an orthogonal goal that we pursued while looking at Autobahn was that we wanted the design to be not just simple, but also modular, meaning that you can actually plug in your favorite BFT protocol in Autobahn's architecture to give it high throughput and makes it seamless. So for whatever reason you're currently deploying hot stuff, for example, you can combine hot stuff with Autobahn to add seamlessness to hot stuff, or replace hot stuff by any BFT protocol you choose. So let me talk about how we do this. At a high level, Autobahn is going to consist of two core components. The first is going to be a data layer that transports batches of transactions at the pace of the network, regardless of interruptions to consensus. And the second is the consensus layer that is going to consume this data layer and reach agreement on its output. Now, separating the data layer from the consensus layer is a well-known idea, and that's not the main contribution of our system. Rather, our challenge lies in finding the right balance and coordination between the two layers. If we offer too few guarantees, then we'll end up with something that is not more seamless than any existing protocols. But if we lump them together, then this is going to come at a significant performance cost. So we really wanted to find the right balance and the right level of interplay between the data layer and the consensus layer to achieve seamlessness, while preserving high throughput and low latency. So what we settled on is that to support seamlessness, our data layer needs to have three key properties. So first, we obviously need to make sure that our data can be reliably retrieved. And that requires us to ensure that at least one correct replica has stored the data. Otherwise, Byzantine replicas can cause us never to recover the data. That's not surprising. In order to avoid hangovers, we also want data dissemination to make as much progress as possible, namely at the pace of the network. I'm going to call this property responsive data dissemination. And finally, we want to be able to easily index or disseminate data so that arbitrarily, independently of the amount of data that has accumulated and has been disseminated, consensus can easily index it and order it all at once. So that's the three properties that we're going to want from this data dissemination layer. Availability, responsive dissemination, meaning that you make progress at the speed of the network always, and this instance referencing property that consensus is going to use to quickly recover from blips. So let's start at the top. The key unit in Autobahn's data layer is a car, which is just a fun way of describing the process of guaranteeing the availability of requests. A car starts with one replica that acts as the proposer, and that proposer is going to broadcast a batch of transactions to everyone in the system. Other replicas are going to store this batch and return a vote to acknowledge that they have stored the data. Once the proposer receives enough votes to ensure that at least one correct replica has stored the batch, it can prove to others using this car certificate that this batch is truly available. Nothing fancy going on here. One thing to highlight, though, is that cars do not provide any stronger guarantees than data availability. Specifically, it is possible for cars to equivocate. That's okay. And the reason for why that's okay is the data layer should be concerned about dissemination, not ordering. What this does is guarantee the data availability, and that keeps the decoupling between consensus and data dissemination very clean. Now, once we have cars, we're going to change them together, just as others have done in the past, into what we call a lane. Specifically, each new car that a proposer creates is going to contain a hash reference to the previous car it created, which implicitly is going to create a total order within a lane. Now, this chaining property is going to allow us to uniquely identify and prove the availability of the entire lane with just the last car. And this is what gives us our instance referencing property. Specifically, because you're including the set of hash references, as long as you have the final tip of the lane, then you know that all previous blocks that were in that lane are also available. And that will give us our instance referencing property. And we care about it because of seamlessness, because we're going to leverage that property to allow consensus to commit long lanes very fast with just using the first car. And we can do so at a cost independent of the length of a lane. Finally, we're going to take the concept of a single lane and expand it so that every replica governs its own lane. Specifically, each lane is going to grow independently of other lanes and without timeouts. Now, having multiple lanes maximizes the throughput and guarantees that dissemination does not hinge on a single proposer. And because that's a problem, because that single proposer might be malicious. Running them independently is then going to minimize coordination and allow us to have flexible proposer speeds, which can be good if you have heterogeneous validators, for example. Now, lanes guarantee a responsive dissemination property, and we care about this seamlessness because we're going to continue growing our lanes even when consensus cannot make progress, as long as data can still go through. Now, usually we get a question here that says, well, what if there's a network partition and data can't go through? Well, there's nothing we can do here. But what we found is that during blips, there's often cases where data can make it through, and there's a progress interruption because of a leader failure, or because there's a partition that doesn't partition the network fully in the middle. So there's a lot of cases where data is still being disseminated, it's just consensus cannot make progress. Okay, so this is how we structure our data dissemination layer. Now we can move on to consensus. So let's first try let's just take a look as to why we even still need consensus. Well, remember that our data layer only provides fairly weak guarantees. And that means that asynchrony or equivocation can cause lane states to diverge between replicas. For example, two replicas here, they don't need to necessarily have the same lane state. So specifically, if you look at the third lane here, replica 1 has 2 blue cars, while replica 2 has nothing. In contrast, if you look at the orange lane at the very bottom, the first replica has seen 4 cars, while the right replica has seen 3 cars and a truck. And that can happen because our lanes, by design, do not guarantee non-equivocation. So we need consensus to be able to reconcile divergent lane state. And this is where the instance referencing property is going to come in handy. So remember that because of instance referencing property, we can uniquely identify an entire lane from just the last car alone. So instead of reaching agreement on cars individually, we're simply going to propose a snapshot of our data layer by using the last car, or the tip, of every lane. So in the example here, the snapshot would be, the tip cut would be green car 2, red car 2, blue car 2, and orange car 3. And this simple tip cut is going to transitively prove the availability of all preceding cars. And in particular, this means that the size of our consensus protocol is going to grow as a function of the number of lanes, but is going to be always independent of the size of the backlog, which is vital for guaranteeing seamlessness, because that's what we want to immediately commit any backlog data that arose during a blip. So tips give us succinct snapshots, and that's great. Now let's just say that we propose this tip cut here. So the obvious question is, when should you create new tip cuts? Now ultimately, consensus works on data. There's no point in doing consensus on data that you don't have. And so we're always going to want to make sure that we do a new consensus instance when there's new data to propose. Now, obviously, because some lanes might be malicious up to F, we don't want to wait for all lanes to have new data. So the halfway point that we found is that we're going to propose new tip cuts when you have n minus F lanes that have new information, Yn minus stuff, because this guarantees that a majority of new data comes from honest proposals. But this is configurable. You can configure it to account for different bandwidth between lanes, reputation schemes, so on and so forth. And we have lots more details about that on the paper. So you'll notice that I'm slowly running out of time, and I haven't mentioned how we reach agreement. Now, I'd love to sort of tell you more about the specific protocol that we use, but I don't have time to go into details. So learning about it is one of the many pleasures you'll get by reading our paper, hopefully, or the many headaches, depending. But you can very much think of it as a pretty standard PBFT protocol. We have an option for it to be linear, so like SBFT, or we can be quadratic, like PBFT. And what I want to point out instead is a couple of sort of features that I find cool. The first is that our data synchronization subprotocol takes advantage of our lane structure to provide the guarantee that you can fetch missing data in just a single round trip. Now, obviously, if you have to download 10 gigabytes of data, that's still going to be slow, but you can identify where the data is in a single round trip. The second benefit that we have is that there's a number of additional optimizations that we do to minimize latency. So this includes, amongst other things, a commit fast path and pipelining, such that when you take the quadratic version of the consensus protocol, we can have optimal message latency. So we can have 3 message delays in the good case when you have the fast path, and 4 message delays when you go slow path. Add a couple of extra message delays if you want the linear version of PBFT. And the last aspect is that just because I'm saying you can switch PBFT and from linear PBFT to quadratic PBFT, we can actually keep the system modular, meaning that we can instantiate the Autobahn framework with multiple consensus protocols. So you can use the same lane structure and run PBFT. You can use the same structure and run SBFT or others. And that was by design. We wanted to very much separate the data dissemination layer from the act of agreeing on tip cuts. The last aspect is execution, and that's nothing very challenging here. So once a tip cut becomes committed, replicas can commit and order all cars and the transactions that precede the tip cut. So how do you order the cars? Well, that's not a very hard thing. Because everyone agrees on the same tip cut, that you can use any deterministic function to interleave the various lanes with respect to each other, come to the conclusion of the same total order, and then execute it. You can execute it using the whatever execute engine you might want. So before I end, just want to show you some brief experimental results. So we evaluated Autobahn against protocols in 2 categories. So the first is, I would say, the traditional star BFT protocols, like Hotstar, for example. So they have really good latency, but they do not separate data dissemination from consensus, and as a result, as we showed already, they struggle with seamlessness. We also evaluated a variant of Hotstuff that tries to naively separate data dissemination from consensus, but this design also doesn't guarantee seamlessness. Now, I'll call those vanilla Hotstuff and batch Hotstuff, respectively. The second class of protocols that we looked at is Bullshark, and that's a state-of-the-art protocol for achieving high throughput specifically, and it sort of descends from the family of DAG BFT protocols that have become popular in recent years. And those are almost seamless, but not quite, and I'll leave that as an asterisk. Feel free to, we can discuss this offline, but from the point of view of this talk, I'll just consider them as seamless. And those achieve high throughput, but struggle with achieving good latency. So onto the numbers. For our first experiment, we showed a throughput latency graph. And we do this in an ideal fault-free scenario. So a throughput latency graph, for those of you unfamiliar, works like this. You increase the number of clients. This increases the throughput that your system has, which is what's going up on the right. And at some point, you're going to hit saturation, which is going to cause latency to spike up. And so the number that matters is the number before latency starts to spike up, which is the peak throughput that you can get, and that's the latency that you'll have under stable conditions. So Autobahn, shown in green, is able to match the throughput of Bullshark, shown in blue, while also having latency that is comparable to Hotstuff. And compared to Bullshark, this means that like, Autobahn's latency is over 2 times better without making sacrifices in terms of throughput. Most importantly, Autobahn's pitch was not just about performance, but it was really about recovery from blips. And since we already showed you that how hot stuff deals with a replica failure earlier, let's just quickly revisit this example with Autobahn. So we had a leader failure. We increased the blip duration slightly, but the takeaway remains the same. Hot stuff in blue is going to suffer from a significant hangover, which is even longer than the blip duration, because it did not optimize for seamlessness. In contrast, Autobahn, shown in orange, returns to the baseline latency immediately as promised, aka immediately as the blip ends. And so we are able to achieve seamlessness. So that brings us to the end of sort of the Autobahn overview. So I want to briefly summarize. So Autobahn shows us how to build a BFT system that is not just efficient under partial synchrony, in theory, but also in practice. It matches performance of existing BFT protocols, but has much better robustness. And what we like is that it's simple, meaning that you don't need to start from scratch, but you can already build around the core that you already have. Now, Autobahn has been adopted in production by a number of companies, which we're pretty excited about. Say Commonwealth Older Broadcast, Beharvest, Inform Insomnia Chain, Hiller. So if you're thinking about what consensus protocol to pick, we'd love to chat, and we'd love to see how we can motorize your existing consensus protocol rather than tell you how to replace your existing consensus protocol. So if you have any questions, we'd love to chat more. Neil, who is one of the lead PhD authors, is in the room here. Florian is available remotely. If you don't have any questions, but you want to give Neil an academic job or an industrial research job, just talk to him anyways. But thank you.
If you're waiting for every lane to have at least one new transaction before you do a cut, couldn't this get inefficient if like some of the replicas either don't have new transactions to offer, or if like they're all offering like the same transactions, so you have a huge amount of redundancy across the lanes?
I think at the end of the day, there's two issues. There's the issues of duplicate transactions that we don't solve, and as far as I know, that's a problem in most systems unless you try to, before submitting the transaction, do some amount of deduplication. That is a problem here. The second part of the question is this is configurable. So it is perfectly fine to say that I'm going to do consensus every k unit of time, and that is going to confirm that the lack of progress is important. You can do it optimistically if you think that you trust the lanes have been reputable, and you can do it as soon as you have one more element. It's a completely configurable parameter, so whatever works for your system.
For the car, to chain it, do you have to give the certificates of the last one back to the next people to verify that and then give you attestation back, or how does that work?
Yeah, so the proposals includes the
proposer includes the last certificate.
Yes.
To the next proposal.
So each lane is one validator, and so when you do when you create a car, you include a reference to the previous car, and the certificate that you have from the previous car.
I see. Thank you.
I'm just wondering if there's any particular reason that you didn't choose to compare with dispersed ledger that has the same idea of separating data dissemination using VID from consensus, making it leaderless so that each node can disseminate its own data, and also I think the lane aggregation idea, which is basically for each person to disseminate their own data, but having a consensus only for agreeing on like progress across the board, like the envelope of dissemination progress. I think the only difference I perceive, since I'm a co-author, is that dispersed ledger is in the asynchrony setting.
Yeah, so it's a fast-moving space, and so we try to do a good job by comparing against representative style protocols. Specifically, that's why we picked hot stuff on one, and Bullshark on the other. I also think it was very, if I remember correctly, almost concurrent work, so we didn't have the thing available.
MSDI 2022.
Yeah, so I think by the time that we were building Autobahn, it was like this. And I think we made the decision to just have partially synchronous protocols as a way to make a clean cut.
Makes sense.
All right, maybe we can postpone the remaining questions. We thank you very much, Natacha, first of all. After this, we have another session with 3 talks on high-throughput protocols, so you'll have a lot of questions to ask about high-throughput and comparing protocols to each other and so on. We'll start the next session in half an hour, so 3:30 we'll start.
All right. Let's get ready for the last session. It's happening. It's happening. It just takes a few minutes. Could somebody close the door? Okay. Welcome everybody to the fourth and last session, technical issues. There we go. Welcome everybody to the fourth and last session of the Consensus Workshop. We have 3 talks in this session, and we start out with Victor Shoup. Victor Shoup is a principal research scientist at Off-Chain Labs and a professor emeritus at NYU. And today he will be talking about Kudzu, which you've already heard in the morning session a lot about. And yeah, he'll fill in all the details in the afternoon now.
Yes, so Kudzu is a very fast-growing invasive plant from Japan. It's a fast-growing weed, so there seems to be a theme of plants in this space, so that's our plant. So this is going to be a protocol in the partially synchronous blockchain-style consensus model, same model as PBFT, really. We have n parties, less than a third are corrupt. Liveness means we only have liveness during periods of synchrony. Safety, always. Thank you. And I'm going to introduce you to Kudzu by way of 2 other protocols. So the first protocol is, that I'll talk about is Simplex. This is a beautiful protocol from a couple of years ago. It's simple, and it's objectively simple. And it has optimal latency, only if you just think about latency, at least in a theoretical sense of just network hops. A big problem with it is its communication complexity is pretty bad. On the one hand, if you take it like completely literally, if you like read the paper and see what's in there is the leader in every round has to broadcast the entire blockchain back to the genesis block to every other party. And then every party then echoes the entire blockchain to every other party. So that's clearly, I mean, that's what's in there. And so it takes just a little bit of thinking to see how you would make something slightly better than that. But even if you do that, the communication complexity is pretty bad in the sense that there's this leader bottleneck where the leader is broadcasting a block to all parties. And it's well known that this causes problems. Dispersed simplex is a little thing that I wrote a couple of years ago as well, inspired by simplex and some, at least by the name dispersed ledger. I proposed adding some features here. So it's still objectively simple, and it has the same latency as simplex, and it has good communication complexity. And good meaning like small, and also so there's no leader bottleneck, and it's balanced. So every party is including the leader is sending out the same amount of data on the network. And this ignores things like all-to-all communication. If the blocks are big enough, then the all-to-all broadcasting of certificates and signature shares doesn't really matter at all, right? So all of this whole line of work about linear complexity is kind of not really relevant to practice, at least for large enough blocks. And then Kudzu is recent work which I did with these guys, and that's the end point of today's discussion. So basically, this has all of the nice properties here, plus there's an optimistic fast path which gives you even better latency under optimistic conditions. Okay, so quick introduction to simplex. I'll just give you kind of a graphical view of like what the blockchain or the block tree looks like. So I started, we have slots here, or call them views or rounds, whatever you want to call them. So I've started off here with like a snapshot in time where I have one certified block, so there's a BC, a block cert for it. And it's also been finalized. Okay, so this is our starting point. Probably lots of other stuff happened back here. But then, okay, in the next slot, the leader proposes a block, and it gets certified eventually. Say the next slot, nothing gets certified, but a timeout occurs, right? So we're in the partially synchronous model, and there's a built-in timeout threshold that can trigger. And if enough people vote for a timeout, you'll end up with a timeout certificate. So in the next round, say, the leader proposes another block, and the rule is, blocks have to point to a predecessor, and you can point to your previous predecessor. You can point arbitrarily far back in the chain, but the rule is you're not allowed to, if you skip a slot, you can only skip it if there's a timeout certificate there. And the leader doesn't broadcast the timeout certificate. It just knows that if it sees the timeout certificate, everybody else will eventually see a timeout certificate. So they'll vote for his block when they see the necessary timeout certificates. So now, say what happens in this round is that it can very well happen that a block gets certified, but a timeout certificate is also generated. That can also happen. In the next slot, I've shown you again here a block that gets certified. It actually jumps over 2 slots because there's 2 timeout certificates, so it can do that. And say in this round, we might actually get a finalization certificate. Oops, I went too far. Finalization certificate. And as is typical in these types of protocols, this implicitly finalizes everything on the path back to, well, and including what was previously finalized, right? So this guy here gets implicitly finalized. Okay, so that's simplex at a high level, slightly lower level. In each slot, there's like 3 rounds of communication. First round, leader proposes a block. Second round, there's an all-to-all voting that occurs. So all parties, when they receive the block, will send everybody else a vote for that block. And we can implement that rule that you only vote for a block if you've seen timeout certificates for any skipped blocks. That'll automatically enforce this skipping rule. And then each party will finish the slot when either it sees a block certificate or a timeout certificate. Then it will move on to the next slot. In parallel with the beginning of the next slot, though, there's a voting round, a second voting round of finalization votes that will be used. So the rule is you only vote for finality on a block only if you didn't vote for a timeout. And that automatically gives you a nice quorum intersection property because you'll never vote for a timeout and a finalization. No party will vote for both. And because of that, these buttons are a little bit tricky. You can't get both a finalization certificate and a timeout certificate in the same slot. And by the skipping rule, that means something that's been finalized can never be skipped. And that's what gives you safety, basically. That's the whole argument for safety. So that's simplex in a nutshell. I love it because it's so simple. Again, objectively so. And I think that if you're going to teach one partially synchronous consensus protocol, this is the one you should teach. And I didn't invent it, so I'm just saying it's just really cool. What's that? I'm just saying this is objectively the simplest, most elegant protocol there is. You can't hide from the truth. Okay, so dispersed simplex is just a simple idea that I cooked up, just kind of obvious, and I don't even think it's that great. But so I said the leader can become a bottleneck in practice. So the obvious way to eliminate that bottleneck is to use erasure codes. So if the block has data, there's some metadata, but then the transactions themselves form some big, 4 megabyte block of data. So you're going to erasure code that up into n fragments. And then the leader is going to include in the proposal message just the fragment for the ith party, so just one fragment. And then each party, when he votes, is just going to include his own fragment and broadcast that to everybody. And so by the end of the voting round, you've already, when you certify the block, you guarantee that there's enough good parties holding fragments and who broadcast them that everybody will eventually be able to reconstruct this, this block. And then each party, so okay, the observation then is that each party, and if you're careful about it, including the leader, each party, including the leader, is just going to transmit total number of bits equal to 3 times the data size. So it gives you kind of perfectly balanced communication. Okay, there's this 3 here, which is a little bit annoying. It'd be nice if it were 1. There's a variant in this paper with a stable leader that actually gives you 1.5. So that could be nice in practice. And again, I'll just emphasize, no leader bottleneck, right? So in practice, that's like the whole thing, right? I mean, you don't, so the whole motivation for looking at DAG-based protocols and car-based protocols, I mean, I do appreciate the fact that the whole hangover problem is an interesting thing, that there are clear trade-offs here. But the motivation for DAG seemed to be that, oh, well, we want to have balanced communication. Well, one way to have balanced communication is to use a balanced data dissemination protocol and a leader-based protocol. So you don't have to trade off leader for leaderless just to get balanced. There are other reasons, though, for like hangovers to look at leaderless protocols. So like, if nothing else you get out of this talk, that's the main thing. Like, leaderless protocols don't have to have leader bottlenecks. End of story, right? So it's kind of just kind of some misinformation that's maybe slowly we're slowly getting rid of. So Kudzu, what is Kudzu? We want to add a fast path, right? So here we have, between the time the leader proposals, there's a total of 3 network hops: propose, vote, and finalize. And it would be nice if we could already finalize at the end of the voting round. And there's a whole long history, somewhat sad history of buggy protocols proposing these fast paths, many of which have been broken, repaired. Dare I say, even hydrangea. Where's that hydrangea people are here? Yes. You represent them? So there was even a liveness bug in the initial version of their thing, which they can be complicated protocols. They can be complicated protocols. But Kudzu, yes, is simple. So the basic idea though behind all of these protocols is that we want to get some kind of a fast finality certificate, which is just going to be comprised of sufficiently many properly defined votes. Right? If we see n votes, then we should be able to finalize this sucker, right, without waiting for anything else, right? Well, okay, that's the basic idea in all of these protocols. And if we can do that, then of course we can finalize right here without waiting until we get over here. The problem is, the way I've defined, if that's the only change I made to simplex or dispersed simplex, you could end up getting a fast finality certificate and a timeout certificate at the same time. Because everybody's broadcasting, say, a vote, but then these votes get stuck in the ether for a minute, and then everybody generates a timeout vote, and now you have n votes for timeout and n votes for a block, and well, there's nothing that you can do to stop people from seeing both of those, right? So this breaks the whole safety argument, right? We weren't supposed to be able to finalize and get a timeout certificate at the same time, because that allows people to skip, that would allow people to skip finalized blocks. Okay. Solution, partial solution. Okay, well, let's change the logic so that we vote for either a block or a timeout, but not both. Well, then automatically we can't get a FFC and a TOC, right? But then the problem with this is liveness, huh? Well, there's no guarantee that you do anything then, right? half the people vote for timeout, half the people vote for a block, and you don't form a certificate for either one, so you don't get out of the slot. Okay, so then we have to introduce complicated progress certificates and other, no, we don't do that. We do something very simple because that's the main thing, right? So the idea is that we're just gonna, if after we vote for either a timeout or a fast finality certificate, I mean, we'll move on if we get one of these, as usual, but we'll also cast some secondary votes under the right conditions, but they're simple conditions, okay? So, and these are secondary, the only weird thing is, these are secondary votes, not to be confused with these initial votes, right? So the FF, you can't get a fast final, so if I vote for something else, you can't get a fast finality certificate out of those things. They won't, they're not in the same category of objects, right? So they're just secondary votes. So there's two different types of secondary votes. One is if I'm stuck here waiting, but then I see a bunch of votes. I'm not going to tell you exactly how many, but I see a bunch of votes for a block. And it's a block that I didn't vote for before. Maybe I just voted for a timeout before. Or maybe I voted for one block because the leader was malicious and is equivocating, but I see many votes for another block. I'm going to jump on the bandwagon and vote for that one too. Okay? So, and that'll be my secondary vote. And the other secondary vote that I can cast is a secondary vote for a timeout. If I see a very simple yet carefully defined notion of a diversity of votes, if I see that there's a diversity of votes, then I will vote for a timeout. And the idea here is that this condition here is defined in such a way that I can't vote for a timeout if somebody was going to fast finalize. But it's just a simple inequality. I just look at my votes, I count them up, and if I see the right number of votes of a certain type, I'll just vote for a timeout. So that's it. So there's no like fancy progress certificates. This is literally just saying, oh, I've seen this many votes of that type, vote for a block. I've seen this many votes of another type, okay, vote for a timeout. And that's it. So I'm not going to go into more of the details here. You can read the paper. It's all very simple. So in conclusion, Kudzu is simple like simplex. It has optimal latency like simplex, if just in the pure theoretical counting the number of network hops version. But also, like dispersed simplex, it has good and balanced communication complexity, which means when you take into account the effect on delay of both bounded bandwidth, network bandwidth, and network delay, network latency, you can still get very high throughput without sacrificing latency. And again, each party, including the leader, is just going to transmit the same relatively small number of bits. And it also adds a fast path. So in detail, it's this. We've seen this, this expression before today. You have F corrupt parties, this extra parameter P. And if you'll finalize in time just 2 network hops if at most P parties are corrupt. And otherwise, you'll still, just as normal, finalize in 3 network hops. And that's it. I have plenty of time for questions.
So these protocols obviously get simpler and simpler. That's clear. But like, why is this simpler than in PBFT when you, because like voting for a view change is like voting for a timeout. We can kind of make that relation, or you do a vote.
Well, and of course, I didn't really talk about view changes at all here. So
that's a timeout. That's a sort of a timeout certificate where something happens. Yeah.
Yeah, but if you get it right. So first of all, there's different ways of implementing this. You can actually have a view change every round. So it's more like a hot stuff kind of style where you can change leaders in every round if you like. There's no special sub-protocol for doing that. And in terms of comparing to PBFT, I mean, PBFT has a, you know, quote unquote, notoriously somewhat complicated view change protocol. This is just you collect a timeout certificate, then you move on, and there's nothing else that you need to do. The only thing that, and it's all taken care of, and this is simplex, right? It's all taken care of by the timeout certificate, the interaction between the impossibility of getting timeout and finalization certificate and the skipping rule that doesn't allow you to skip over, that only allows you to skip over slots where a timeout certificate is formed. And this like drastically simplifies the whole view change business so that it becomes quite easy.
In the skipping rule, do you need to provide multiple timeout certificates?
Right. So,
only the latest one?
no. You don't. You as the leader, you don't provide any. You just go on with firm in the knowledge that if you've seen it's because all these protocols have the property. If I've seen these 5 timeout certificates, then you will see them too. This is the way that everybody's echoing around these timeout certificates. There's a fundamental property is if any honest party sees a timeout certificate, they'll broadcast it and every other party will see it immediately.
I see. But the individual parties do need the whole sequence of skipped slots, timeout certificates.
Yeah, they'll have to remember them.
The leader doesn't broadcast.
The leader doesn't broadcast them, but they'll store those. So for every slot, you'll store a block and maybe a timeout certificate, one or the other or both. And yes, it's important that you just don't forget those things.
On the networking side, with the leaderless setup, is there an optimal number of shards or kind of network participants that you send components to? Or is there an optimal network topology? Because for leader-based protocols, what I've noticed is that stake weighting in a tree with, I guess co-located node is probably like the easiest way. I'm just curious.
This only really makes sense in a setting where you have n equally weighted parties talking to each other over point-to-point channels. If you have overlay networks, if you have weighted stake, I don't even, maybe people can tell me, I don't know if you have weighted stake, I mean, actually Alpenglow does this, so maybe they'll talk about this. If combining weighted stake with sharding is actually a complication that Solana has solved, I guess. So that's something that maybe Roger will talk about next.
I think to Marco's question, the difference with PBFT, which might be a moot point in practice, but is that here, if you have like bad network conditions, you can keep not making progress, meaning you don't commit anything, but the state you have to keep grows linearly because you have to keep all those timeout certificates.
Oh,
and so
yeah.
your state is unbounded in some way, right? Even though you're not making progress. But it's probably not a big deal in practice because you're not going to have super long periods of no progress.
I mean, in practice, you would probably do something anyway, like start increasing your timeout interval so that you do start making progress. But yeah, there's a number. Simplex isn't the only protocol with this property, but yeah, if you're saying that in some protocols like PBFT, you might not finalize everything. Wait, is that true? But you'll say you'll be building up some state that you can finalize?
So in PBFT, even if you have a really long period where the network is asynchronous and you can't finalize and you keep starting new views that don't make progress, you only remember a constant amount of information about all those views. Whereas here, you remember a linear amount of information per view that doesn't make progress. Right?
Yeah, okay, that's fair, yeah. That's a fair criticism. I don't know if it's a deal breaker, but it's a fair criticism. I don't know, yeah.
We have to make the protocol more complex to deal with that.
Yeah. Darn it, well, okay.
Cool.
Implementation.
One more question.
Before I ask, I'll just say I'm also a big fan of Simplex. So, you've been working on Simplex, like thinking about and researching into Simplex for some number of years now, at least from your dispersed Simplex work into this. I'm curious if there's a particular direction you think it takes from here, like the Simplex style of approach, like if you have new, twists and turns following Kudzu, following all this work you've done in this direction.
I don't know, but there's like, okay, I'll throw out one open question here, is that, which we don't know how to solve really, is like, for this basic dispersed simplex without the fast path, you can, with a stable leader, you can reduce this constant 3 to 1.5, so you can get better data dissemination rates. Here, I don't know how to do that. So there's one little open, it's not a visionary, directional type of thing, but that's like the one open question I can see. Yeah.
Cool. Let's thank Victor one more time. I guess we should have titled this session Simplex. Simplex Help Group. Cool. Please join me in welcoming our second speaker of this session, Roger Wattenhofer. He is a professor at ETH Zurich, and he's also the head of research of ANSA, which is the development company associated with Solana. And today he will tell us exciting stuff going on in the Solana ecosystem, namely the new Alpenglow consensus protocol.
Cool, thanks. Hey, nice applause. So yeah, this is about the Alpenglow consensus protocol, which hopefully will be the new Solana protocol. Maybe Solana doesn't have the best reputation for consensus. I don't know how you feel about this, but this maybe should solve it. So if you have flashbacks during my talk and you think this sounds a bit like Kudzu, so this is the fabulous Alpenkudzu. So there's 3 authors on both papers, and actually one author is shared. So he probably was a double agent between the 2 projects. And we don't quite know on which side he spied more, but many of the ideas are basically in both papers. So let's go back to Solana. What we want to have in Solana is we want to have high bandwidth and low latency. And I would say Solana is actually very good already regarding bandwidth. So we can put together, Solana has this erasure code system for many years now. You can actually add more machines, as many as you like, with different bandwidth, and it will work out nicely. But latency was, in some sense, was reasonable with Solana, but it's much better with Alpenglow. And the second thing we wanted to solve is security. So that's maybe a bit of a problem with Solana in the previous form. With Alpenglow, we get this 20 plus 20 security, which is basically the same thing as the 3F plus 2P, which is plus 1 we just seen. We just called it like that. It's a bit catchier marketing-wise. So we can tolerate 20% Byzantine stake and 20% crash failures or slow nodes or something like on top of that. So maybe up to 40% failures, which is a bit more than the usual holy 3F plus 1 thing on this side. We think that the Byzantine failures are maybe a bit overrated in this community, okay? So 33% attacks in Solana would cost you literally billions of US dollars. So who is going to do that, right? Who is going to risk that much money? So we hardly ever see them, but crash failures we actually see quite a lot. So to have a higher crash tolerance is actually something we like. And maybe you know this meme about the Argentinian president, and apologies for the people who have seen this talk before or similar talks. So where he kind of rips off all the ministries in Argentina to make Argentina better, I guess. So we have the same thing for Solana. This is basically the consensus protocol of Solana today. These are like maybe the 4 cornerstones. Maybe you've heard of proof of history. Oh, maybe this one goes first. Tower BFT, we don't need it anymore. It was not very good. Proof of history, Victor actually wrote a nice paper about proof of history if you want to know about that. Solana uses gossip, which is also something I don't like so much. We try to not use it anymore in the future. We think there's faster communication than gossip, so this is gone. And Turbine is the one, the erasure coding part, which we really like. We kind of keep this. We're going to simplify it to Rotor. So that's what we use. And on the voting side, we basically were inspired by some recent work, I would say. And as I said, Kudzu is sort of related to Alpenglow, and we have the same inspiration to some sense. We have the original Simplex consensus, which is simple, but I still think it's a really bad name, okay? So why did they choose a name? You know, there's like 10 algorithms that people know in the whole world in computer science, and the Simplex algorithm is one of those 10 algorithms. Why do you use the same name? I don't get it. Okay, so we have this dispersed Simplex, and then on the right-hand side, that's something Victor didn't mention, by Jan, who's in the audience, and others, which is probably the first paper which has this idea that you can do 2-round voting and 1-round voting right from the beginning, right? So this idea was around for a long time that you can do a 1-round voting protocol, And if it fails, then you can do a slower 2-round voting protocol. But Banyan was the first one that actually started both protocols at the same time. Banyan also had its problems, but I think this is, we should mention that. So these are maybe the 3 inspirations for us. And this becomes the voter protocol, which stuck as a name, even though it was a joke. So we have voter and rotor, and I'm going to explain them quickly. And sorry, here I went a bit overboard with the animations. But so rotor is the data dissemination protocol. So what we have are blocks, basically, like you would think of a leader-based blockchain protocol where the leader can change over time. So we produce one block after the other. The blocks themselves, they are used for the consensus, and then each block, let's look at one block here in particular, is split up into slices. So slices are just like small blocks, and we use them for pipelining. So we can distribute the data of the slices very quickly, and we can execute that already. And so we can do this in a pipeline fashion. So that's what is very important to us. And each slice then itself is basically coded into shreds. So you just take the information of one slice, the data information, and you make a few shreds of them. And we're going to erasure code those shreds, which means we don't just send around these shreds that are basically a slice, but we, let's say, double the data. Okay, that would be over-provisioning of factor of 2. So we have heard before 1.5 is maybe possible. 3 is also, has also advantages. So we chose 2, but there's no good reason for that. Maybe history, because Solana has always used 2. So these shreds then are being disseminated. So we have always a leader of the current block, which produces these slices and then sends these shreds for each slice out. These shreds go to relays. The relays are basically all the other Solana nodes chosen by their stake. So with the probability of their stake. So if a Solana node has, let's say, 2% of the stake, there's a 2% chance that you get such a relay. If somebody has a lot of stake, can also get multiple relays. Then if you are a relay, you just send your shred to all the others, okay? So you can use fancy multicast for that, but it also works just to send to everybody. So this hurt me a little bit when I saw this first time, or when we kind of came up with the idea to do this like this, because you always will think, oh, let's make a complicated multi-level tree structure, because why would I send, so let's say 2,000 nodes? But sending the 2,000 nodes takes a few milliseconds. On Solana, we have fast internet. And just having one more leg that you just send to somebody else who then sends to somebody else, that's already maybe 50, 60 milliseconds, so it's much, much slower. So this is actually the fastest way you can do this. So this is basically you send just to all the other nodes. And think of something like 2,000 nodes. We don't have much more for Solana. Good. Well, my voice, I don't know why this happens now. So we want to incentivize participation. So this is actually the biggest cost factor that we have in terms of bandwidth to send out these shreds. The leader does not have much bandwidth here, actually, just has to send each shred exactly once, but then each relay has to send to 2,000 nodes, so that's basically 2,000 UDP packets. Everything we send around is at most 1 UDP packet. So this is the question we had before, what would be the over-provisioning? So we made a few simulations with the current Solana stake distribution in the world. So let's say if you have 32 shreds for each slice, and now the question is how many total shreds should we send out? Maybe let me go quickly here. So we could double like here, or we could even 10x it, right? So that's possible. And you see the red line here basically is how much latency we would have if we just send directly from the leader to any receiver, okay? If we had enough bandwidth to do that. And now, as it's clear, kind of if you over-provision more, then you have more direct paths, okay? Because you only need 32 shreds to get the whole block together again. So if you send 320 shreds to relays, you only need 32 of them, then chances are that these relays are on the path basically between leader and receiver, okay, for any receiver. And that's why the latency here is not much worse than just sending directly. But we will choose a factor of 2, and it gives you something a little bit more than 100 milliseconds here. And this is maybe one of the reasons I don't like these delta calculations so much. So many people talk about delta. That's sort of like another holy cow in this whole space, right? We have the 3f+1, we have these deltas. The reality is not with deltas, okay? So we have to I think it would be much better to look at something else. I mean, the deltas and the 3f+1s, they come from a time when the n machines are basically in the same room or something like that, right? But in a worldwide distributed system, we don't have that anymore. So I think it would be great to be more fine-grained here. Now the voting part, so Victor spent some time on that. I'm going to be very fast on this, okay? So what we want is this kind of blockchain. We have leaders making a few blocks, so this is what this picture here shows. So every leader basically makes 4 blocks and then gives the baton to the next leader. And now we have this timeout. So it used to be proof of history, which nobody really understood. Actually, it's still that, but hopefully not for much longer. So now we have every other participant, every validator, every node, basically checks from the time that they received the certificate for the last block from the previous leader until this next leader. How long are they willing to wait for these rotor disseminated shreds and slices, and that gives a timeout. So they can just vote yes or no, essentially, based on this block. This is what Victor called the first round vote. So we also have timeouts for the previous blocks for the same leader, and the reason is if one of those leaders is not working well, not participating how they should, we can actually vote them off much earlier, okay? So if block B1 is not coming in time, then the whole leader window for that leader will be gone, and we immediately go to leader C. So we send out this vote. Let's say this block came in time. We have this plus vote here, and we again send this to everybody, okay? That's a small message which can just send out in a few milliseconds, not much overhead. We also want to give some money for the votes. Actually, there's a common theme here. So we really want to incentivize the whole protocol, okay? So in many of these blockchain protocols, the participants basically do work, and there's no real reason why we should do this work, right? But we kind of want to incentivize the whole participation chain. So when you get these votes, then you could have this situation. This is just a recap from what Victor said. So you could have a lot of upvotes. Let's say if you see at least 80% of the stake voting for a particular block, meaning that it was correct and came in time, then you immediately finalize, okay? You get this finalization certificate, which is a BLS certificate. Also fits nicely into a single UDP message. You just send it to everybody. Everybody can finalize as soon as they construct a BLS certificate or they get it from somebody. In the other extreme case, we have a lot of downvotes. They don't want that, and then we only need 60% downvotes, and that immediately gives us this skip certificate. Same thing, that's coming from Simplex, which we also can say this block is skipped. We don't have to talk about it anymore. Now, also that is sent out. So the mixed case is the most interesting case in the middle, where you have a bunch of upvotes, a bunch of downvotes that you get. Now, if, let's say, if you have the case that you get 60% upvotes, that would be also a typical case, okay? So that would be the case where we go into the second round, that we actually send an explicit finalization vote around. But for all mixed cases, we basically have a second round, okay? So that's what we do. For the 2 corner cases, we just have 1 round of voting, but in the middle, you have a second round of voting. So the hope is that this basically never happens, okay? But we'll see in a second, this can, of course, happen. We call these modes fallback votes. So when you say voted yes, but you don't see that the certificate for yes is coming, and you have a timeout eventually, then you're also going to say, I'm also fine with no, okay? That's exactly what Victor said as well. So you have these fallback votes. You can basically change your opinion to the other side, okay? You cannot reinforce your side. You can only change the opinion. So that you support also the other, liveness possibility. Okay, not sure how I'm going with time. Fine, right? So this is a paper you can read. So this is like the white paper that came out May 19th from ANSA. There's also the double agent here. And we recently updated it to version 1.1, where we have, let's say, something like a related work actually inside. The original paper doesn't have it. So it's 50 plus pages. It's quite dense. Or maybe not dense, but I would say there's a lot of things in there, and we have a lot of, let's say, practical considerations in there. So for instance, how do we make this change between 2 leaders fast, okay? So if you're a leader yourself, you can just pump out these 4 blocks because you know you're a good guy, right? Everybody will vote for you. And you just optimistically pump out 4 blocks without waiting. But if you have a leader change, then the next leader wants to know whether the last block from the previous leader was in or out, right? And so what they do, for instance, is they start, if they have seen the previous block, they hope that it will be finalized. So they just optimistically say, let me start the block by doing that. But if they then see that there's a skip certificate coming for the previous block, then they can sort of, fail over and send out that after that. Good, so here's a nice slide, a little bit about measurements. So we implemented this to some degree. This is like a simulation implementation, I would say, where we simulate the network. This is basically for a New York-based leader. When you look at the stake at Solana, where the stake is sitting currently, how much latency you have, okay? So you see some nodes here have a lot of latency from New York. Others have almost no. There's some stake which is also in New York directly, right? And actually, this is 200 milliseconds. And these are like usually, let's say, other American nodes here, and then you see a bunch of European nodes. I don't know if you know, but Solana has actually quite a bit of stake in Europe. So there's a long plateau there, and then you have the rest of the world essentially. So this is just the network latency. And now this is basically our lower bound, right? We cannot be faster than this. So now we have this rotor data dissemination, and you see this curve is, at the beginning it's kind of very flat because you need to collect these 32 shreds out of the 64, and this takes time. So even for the people in the US here, there's not too much over-provisioning happening, so some things have to go, let's say, through Europe and back to come back, and then, you see there's a bit of an overhead already here. Then we have the voting phase. So the first part of the voting phase is up to 60% yes votes. This just shows the good case where we have only yes votes. So you see at this point, the nodes have this so-called notarization certificate already, where they would say, looks good, but we have one more round of voting. And now this is when you have finality here. So either this can have several ways to get here. So either you basically go up to 80% votes from the first round, right? At this point you collected 60% of the stake, but it takes a bit longer to take 80%. Or it could be that you had a second round of voting, so you had 60% of votes in, then you send your notarization out, and then you wait for 60% of those. And sometimes that's faster, or sometimes maybe it's even faster that you get the finality certificate from somebody else, okay? So all three paths are possible. And actually the nodes here, some do this, some do that. They can completely mix and match however they want it. And that's sort of the idea of Banyan here implemented. Let me try to finish up. Maybe I was faster than I should have, but I don't know. I've given this talk so much, I get faster every time. So there's some open problems, and I would say, so these are the two biggest ones, okay? So that's a problem for us, I guess, for our engineers. So we have to now migrate from the current system to this system, okay? And that's not so easy, okay? So I would say this is basically changing a running system. So we have seen this from Ethereum maybe 2 years back or something with the merge. And so this is, I would say, one of the biggest engineering feats you can have in computer science, right? That you have to change a running system with thousands of nodes into a different running system. So we'll have this problem. And I hope it works, otherwise I'm going to get some of the blame, I guess. And then the second big problem, I would say, is incentives. So I mentioned this before already, that we really want to incentivize the whole system. And this is now quite tricky. So far Solana actually sends votes on chain, so everybody sees what everybody else is doing, but this is not very fast, okay? So our system is much faster. And you remember, like we had this rotor and voter data dissemination parts, so we had to send to everybody basically. So the votes go to everybody else, and also the shreds when you relay go to everybody else. So the only people who can judge whether you actually do your work is all the other nodes, okay? So the question is, how do we make sure that everybody works correctly? And this is something we haven't solved so far, I would say. We just make some assumptions and have some simplification so far, but we are working hard to maybe even make that completely, game theoretically correct, in the sense that, you collect what others have been telling about others, and then you make a decision how much SOL everybody should get in this protocol. Good. So this is just a related to this point. So you see here how much bandwidth you're going to use. Let's say if you want to have something like 500 megabits per second good put in terms of transactions. So that's a high number, but that's something we really should be able to achieve. And you can see here, this is a logarithmic scale, so it's a bit complicated to see. Again, on the x-axis, we have the sort of stake, like some nodes are highly staked, some nodes are not so highly staked. Regarding voting, what the voter part is, everybody has to do the same work. So they send about 30 megabits per second data around just to vote on the blocks. And then you have the router part, which for the really high stake nodes, they have to send around a lot of traffic. However, these people, these are professionals, right? So they have thousands of machines actually. And the router part is nice because you don't need one machine to do that work for you. Basically what you get is a shred from somebody and then you just send it to everybody else, right? So you can completely, there's no signature here or anything you have to do. You just get what you get in, you send out, right? So that's a very fast thing you can actually replicate nicely without state. Good, yeah, maybe one more slide on this and then I'm done, yeah. So, yeah, this is a meme, maybe I should explain it. So when you talk to validators, they would say something like this, right? We're not Byzantine, we try to do the best for our protocol, right? We're also Solana fans or whatnot. And of course I follow the rules, I'm not a Byzantine guy. But when you present something as a game, for instance, when you say, oh, let's report what others are doing, then they start thinking. Then they say, oh, if I say I got less shreds from that guy, then I look better in comparison to that guy. So maybe I should, misreport a little bit. That would be Byzantine, right? That's not doing what you're supposed to do. But sort of like when you present things at the game, then people will see it as a game. So that's sort of like the problem we have a little bit. I'm not saying that they are like that, but you can really, like whenever you propose something, you immediately see their brain starting to work, maybe I can game this. Good, yeah, so that summarizes the whole talk. So I talked about the router and voter, which are the key ingredients of this new Solana consensus protocol, and a bit of statistics and what our main problems are. Thanks for listening.
Any questions?
Why 4 blocks per liter?
That's just historic. So currently it's 4 blocks per liter, and whenever we felt something is not so bad, we just kept it for the moment. This is, however, something we might change in the future. There are arguments to just do 1 block per liter as well, because you can then have less MEV extraction. But on the other hand, you have this like leader change, a bit of a downside. So for us, 4 blocks was kind of a reasonable thing, and we didn't want to change all the things.
Any more questions?
I was on the back.
Could you just summarize like the key differences from Kudzu?
Yeah, so in the paper there's a whole page on this actually. So because when we came out and then the second version Kudzu also came out, and we wanted to do that. I would say the main differences are this is proof of stake. Kudzu is just n nodes, so that's maybe something which is immediately visible. So our bounds look a little bit different. Then we have a lot of thought about corner cases in the paper. So what happens if if you don't make progress for so much time? What would you do then? They don't have that. This is more like an academic paper. Ours is more like a practical paper. But they were both really developed at the same time. So I would not want to say this was first or that was late.
I guess the crash faults as well, right? The crash faults, do you consider crash faults?
No, I think that's the same thing for them, right? They have this 3f plus 2p, and I think they don't specify what f and p is, whereas we just say, let's do 2020, that's good enough. But I think this idea is also in Kudzu.
Cool, let's thank Roger again.
Yeah, thanks.
switch it on. Okay, there we go. There we go. Okay, all good.
I'll give you this when it's 20 minutes in.
Okay, right.
All right, ready for the last talk. This is actually very interesting because, as Roger just pointed out in his previous talk, in Consensus we don't have very good models that allow us to study sort of on an analytical level kind of the performance of these consensus protocols. And well, Andy is going to talk about some step in that direction, so that's going to be very exciting. Yeah, Andy is a professor at London School of Economics. He's also been an advisor to Avalanche, and today he'll talk about the pipes model.
Thanks very much, Joachim. Yeah. So, and thanks also to David, Sarat, and Camilla for organising the workshop. It's been great. So yeah, I'm going to talk about some recent work which with Kartik and Nibesh, which is aimed at addressing what we see as like a significant gap in the literature. Specifically, that's the lack of formal methods for analyzing properties of a blockchain protocol, such as the maximum throughput that it can handle. Okay, so let me explain what I mean by that. So at the moment, if you're going to study a blockchain protocol, a protocol for SMR, there are basically three standard timing models. Right? There's the synchronous, the partially synchronous, and the asynchronous settings. Probably everyone knows what they are. If they don't, it doesn't really matter for this talk. Common to all of these models, though, is basically the fact that they're sort of indifferent to message sizes. Right? We don't really care about message sizes. So in particular, messages are allowed to be of unbounded size. So if you're in the synchronous setting, then a message of any size sent at time t is going to be guaranteed to be delivered by t plus delta. Right? And there are good reasons for this simplification. Basically, we want to keep things nice and simple, obviously, but we want tidy models. And generally, if you're just analyzing basic properties such as consistency and liveness, maybe you can get away with this. But an immediate consequence of that simplification is that we don't really end up with any good way to talk about things like maximum throughput. Right? So if you're in the partially synchronous setting, according to the model, I can form a block with any number of transactions I like, right? Send it at time t, and if we're after GST, then it'll arrive within t plus delta. Yeah? Okay, so we don't have good ways to look at maximum throughput. And it's also a problem when we consider what I'll call the real-world latency. Right? So roughly speaking, by real-world latency, I mean like the time between the first point at which a transaction is received by a correct processor and the point at which it's then finalized by all correct processors. Yeah? So in the standard models, latency is just upper bounded by just counting the number of rounds of communication required. Yeah? So we have 10 rounds of communication required in the synchronous model, then latency is 10 delta. Right? So there's a clear understanding that this is a simplification. This is not realistic. Obviously, in reality, sending larger messages will take longer. So then we have this kind of slightly awkward dance, if you like, in which we also consider communication complexity. In other words, the number of bits required in order to finalize. Right? And that's fine, but then we have no sort of formal way to weigh these metrics. So if I have a protocol that has like lower round latency but higher complexity, what does that mean in terms of real-world latency? We don't know. Right? So for example, consider hot stuff. Maybe it has like a greater round latency but lower communication complexity than 10-bit, for example. Okay, so which actually has real lower latency? We don't know, right? According to the model. Okay, so this is all well understood. I'm not saying anything controversial here. It's all been brought to a head by recent research in which people are looking to develop protocols that really can deal with very high throughputs and that scale well, can deal with large number of processors. So as I'm sure people are aware, right, so there's kind of more traditional protocols which I'll call single sender protocols, protocols like PBFT, where you have a single designated, potentially rotating leader who's responsible for proposing blocks. There's a sort of understanding that, okay, if you've got a single leader, they might act as some sort of bottleneck. Right? Again, it doesn't show up in the models, but there's some kind of understanding this might be true. So there's been lots of research in what I'll call like multi-sender protocols, okay, in which lots of processors distribute lots of proposals in parallel. Okay, so for example, we've got lots of DAG-based protocols like DAG-Rider, Bullshark, Shoup, cordial miners, and then Autobahn that we heard about earlier on as well. Okay. Which you might call a DAG-based protocol or not, but anyway, it's of that sort of flavor. Okay, so yeah, the problem though, okay, so people are interested in these protocols, there's lots of interest in them, but we have no way of formalizing, analyzing this claim, right, that their potentially better use of network bandwidth actually produces better results, better real-world latency, or maybe higher throughputs. Yeah. Okay, so that's the situation. Okay, so we're reluctant to introduce new models into distributed computing for good reason, because we don't want lots of the models all over the place, right? But Okay, we're in a situation here where clearly some sort of slightly more nuanced model is needed. Okay, so our goal in the paper, which is the same title as this talk, so it's the pipes model for latency and throughput analysis, is first of all we want to describe a basic model which allows you to calculate latency as a function of network bandwidth, the number of processors, the incoming transaction rate, and other system parameters. Okay, so I'll describe it a little bit. It's a very simple model, really nothing much to it. With the model in place, it's then easily seen that each protocol has what we'll call a latency bottleneck. Okay, so this is an incoming transaction rate at which latency becomes unbounded over the protocol execution. Right? So maybe transactions just keep on building up and building up. Yeah? So in other words, a maximum throughput that the protocol could handle without unbounded latency. So the model allows us to calculate maximum throughput. Yes, so we'll describe the model first of all, and then obviously our aim is, and this may be slightly harder actually because the model is quite simple, we want to use the model to analyze latency and maximum throughput for state-of-the-art protocols. So in particular, we're interested in asking questions, of the sort, are DAG protocols actually better, or when are they better, and so on. Yeah, and obviously then we also want to run experiments, slightly annoyingly. I hope the experiments are going to be ready by this point, but then they're a few weeks off apparently, okay, so don't shout at me the experiments are there. The experiments are coming. Yeah. Okay, so in the rest of the talk, I'll describe it. It's quite a short talk, so I can't really do many details, but okay. I'll describe the model at a high level, and then we'll talk about results. So first of all, though, I want to sort of talk about some of the simplifications made by the model. There are lots of simplifications made by the model, all of which are maybe interesting to sort of dig into in more detail later on. Maybe you might want to complicate things. So first of all, we're going to focus on the good case, right? The message delivery is reliable and processes that correctly. There are at least two reasons for that. So first of all, real-world experience shows that the good case is actually the common case. If you look at data from real-world blockchains, you'll find that most of the time, most of the nodes are behaving correctly. Right? So that's really the case that you're going to care about most. Right? If one protocol has slightly better worst-case latency, but it's like 3 times slower, then generally speaking, you're probably not going to be interested in that protocol. Another consideration here is that perhaps surprisingly, using the new model makes latency analysis a bit more complicated. I mean, not that much, but it makes it a bit more complicated. So the idea is that by focusing on the good case scenario for latency, we can sort of highlight the results that people are probably most interested in, while keeping things at least reasonably simple. Okay. And then, so there are lots of other simplifications, but another one that I'll just point to right now. So we're not going to consider the time taken to carry out computationally expensive tasks such as signature generation, verification, and erasure coding. Okay, it would be easy to add these things in, and I think we certainly want to do that in the future. But the idea is we're just going to produce the simplest model first of all, and take one step at a time, basically. Okay. And yeah, in the paper we have a list of 8 simplifications, all of which might be interesting to look at, but I'll just mention those 2 for now. Okay, so let's describe the model at quite a high level. So first of all, everything's sort of standard initially. So we have a system of n processors. We're going to imagine there's a channel between each processor, each pair of processors. Processors can be correct, or they could be faulty. We're going to focus on the case that people are behaving correctly. Okay, and then we're going to assume all communication happens in the form of information parcels, each of which is some fixed constant number of bits. Okay, basically for now you can just think of an information parcel as a single bit. Okay, there's nothing really interesting to be said there. Okay, and then message delays. So what I'm talking about here, if you like, is the delay to send a single bit. Okay, we're not yet thinking about how long it takes to send larger messages. Okay, so as standard, time is divided into discrete slots. And the message delay between any 2 processors is always delta time slots. Okay, so first of all, this is for a single information, for a single bit, if you like. It's worth pointing out here that this is a big simplification, right? So in reality, there'll be processors all over the world. There'll be different delays between different pairs of processors. Anyway, despite that fact that's true, we're going to keep things simple for now, and we're going to have the delay will be delta between every pair of processors for now. Okay. Also worth pointing out that we'll be analyzing protocols that might function in partial synchrony or asynchrony, right, where this bound doesn't generally hold. But we're interested in analyzing the good case for now. Okay, you can extend the analysis later on. And then we want to deal with bandwidth. So intuitively, the idea is that each processor should have a bandwidth of S data parcels, if you like, or bits per time slot. It's capable of uploading S parcels and downloading S parcels in each time slot. So how do we formalize that? So we're going to give each processor a single upload buffer and a single download buffer. Okay, so that's really a single buffer per processor. It's not per channel or anything like that. Right? So a single buffer per upload buffer, single download buffer per processor. And you just think of these as being sort of queues, right, in terms of stuff that you want to upload and download. So when a processor executes an instruction to send a message along any of its channels at time slot t, the corresponding parcels are immediately added to this queue, to its upload buffer. Each parcel added to the upload buffer has an intended recipient. Okay, and then at the end of time slot t, S parcels are removed from the upload buffer in a first in, first out fashion, and they then appear on the download buffers of their intended recipients at t plus delta. Okay. Obviously, you're just removing whatever's there. There's less there, you just remove whatever is there. And then at the beginning of a time slot, up to S parcels are removed from the download buffer in a first in, first out manner, and those parcels are then received by the processor, together with information specifying the sender of each parcel. Okay, so nothing surprising there happening. I think it's just very, very simple. We just have these two queues. Okay. Now we have to think a little bit though about so how fast are transactions arriving and where are they arriving. Okay, so what we're going to do, we're going to suppose that the set of processors as a whole, P1 to Pn, they're always going to be receiving transactions at a total combined rate of d parcels or bits, if you like, per time slot. Okay. So that's the set of processors as a whole. Now, though, there are some little sort of, potential complications, right? So the idea is with DAG-based protocols, everybody's supposed to be producing their own blocks. Yeah, and there could be complications there, so maybe there will be some duplication of transactions between different blocks. Maybe some blocks will contain transactions that are incompatible with other transactions and so on. Okay, so there are lots of considerations there that are worth going into. For now, we're going to sweep all of that under the rug, right? And we sort of imagine that basically, when we're considering what I'll call the multi-sender setting, when we're analyzing DAG-based protocols, I'm just going to imagine that the d parcels per time slot are just evenly divided between the n processors. Okay, so they get to d over n each. Okay, somehow. Okay, so okay, so we have these two different settings. So in the single sender setting, which we're using for analyzing your standard sort of protocols like PBFT, I can suppose there's a designated leader that's receiving d transaction parcels at each time slot. In the multi-sender setting, we suppose that each processor receives d over n transaction parcels at each time slot. Okay. Okay, so now let's talk about some results then. So obviously the ultimate aim is we want to be able to establish results for SMR protocols. In order to do that, we kind of have to build up a little bit, basically because a lot of the standard DAG-based protocols use some simpler primitives just for the process of block propagation. Right? They might use consistent broadcast or reliable broadcast just for building the DAG in the first place. Okay. So we're going to build up. So first of all, I want us to focus on the single sender setting, and we'll just look at what I'll call a best effort broadcast, right? Basically just the task of sending blocks directly. Okay, so we're going to consider best effort broadcast, single sender setting. So here a designated leader PL receives d transaction parcels per time slot and sends those all to other processors. Our goal is to consider the rate at which PL can push data to all others in a context where data should be included in blocks that must also contain metadata. Okay, we're going to initially suppose that leaders sending data to others in a straightforward way without using techniques like erasure coding. Okay, so later on we'll come back and we'll talk about erasure coding. Okay, but for now we're not. Okay, so the analysis here is complicated slightly by the fact that we actually turns out we have to consider sort of different forms of metadata. Okay, so we're going to distinguish between what I'll call dependent metadata. This is metadata such as PL's signature on the block, if you like, which can't be determined prior to knowing basically the full content of the block, other than that data. Okay, so you need to know everything that's in the block first before forming that part of the metadata. That's distinguished from independent metadata, which could be determined before maybe knowing everything else in the block. So for example, in some context, you might already know the previous block you're going to point to. Okay, so that would then be independent metadata. Okay, so some notation. I'm going to let M denote the total size of the metadata for each block. Well, the size of so MDE is going to be the size of the dependent metadata, and MIN will be the size of the independent metadata. Okay, so M is just MIN plus MDE. Okay, so then you can prove a formal statement that goes, well, here's an informal version of a theorem. So yeah, so first of all, consider the single sender setting. If the incoming transaction rate is D, then the lowest possible latency you can achieve for best effort broadcast is given by this formula here. You're not required to sort of engage too deeply with this formula. Okay, but to remind you, so M here is the size of the total metadata, N is the number of processes, D is the incoming transaction rate, S is your bandwidth, MDE is the size of the dependent metadata. Anyway, you don't really have to engage with the formula. I'll sort of point out what's important about the formula. Basically, the point here is that, so if ND is small, okay, then the delta term is going to dominate. Okay, but we get a latency bottleneck appearing as ND approaches S, right? Then the latency goes up towards infinity. Okay, so as D approaches S over N, you approach this latency bottleneck. Okay, there's a factor N there, right? Okay. What happens in the multi-sender setting is that you get a similar sort of result, except that now the latency bottleneck appears as S approaches D. So as D approaches S. Yeah. Okay, so the factor N is no longer there. Okay, so now let's explain what's happening in these graphs here. So in these graphs, you've got latency on the y-axis. We've got a fixed incoming transaction rate here, okay, and we're varying n on the x-axis. Actually, both of these have all the same input parameters. This is just a sort of zoomed-in version of this one. Okay, the red is the single-sender protocol, and the green is the multi-sender protocol. I'll explain the purple one in a little bit. Okay, but yeah, so basically what you can see happens here is you get a graph that's kind of like the graphs we saw in Natacha's talk earlier on, where you have latency being sort of fairly stable for a while, but then in the single setting, as you approach a certain point, you reach a sort of latency bottleneck, right? And the latency spikes up. Okay? So yeah, the red is single sender, green is multi-sender. What's happening here is that the latency here depends on exactly how you have to form your DAG, right? So for the multi-sender setting here, we're imagining that you're forming a DAG, but we're not being strict about how you form it. So imagine that each block has to have n pointers to previous blocks. You just point to whatever you see. In the purple one here, we're imagining you're doing what lots of protocols do, where you build your DAG in layers. Okay, so you have to wait for one layer to form, then you form the next layer, and obviously that impacts latency. Okay, so main takeaway. There are actually lots of nuanced considerations there, which we go into in the paper, but for now, the main takeaway is basically the latency bottleneck is a factor n higher in a multi-sender case, okay, kind of as you might expect. Okay. So now, though, let's move on to reliable broadcast, where we'll see completely different things happening. Okay, so I'm going to assume everybody knows reliable broadcast. If you don't worry, because this will be a short bit of the talk. Okay. Okay, so for reliable broadcast, we can do a similar sort of analysis. We get these formulas out here. It doesn't really matter what they mean for now. The important point is that in the case of reliable broadcast, the factor n difference in the latency bottleneck disappears now. Okay? So now we have, it depends how you implement the protocol, but basically here we have a factor 2 difference in where the latency bottleneck appears. And actually you can get rid of that using pipelining if you want to. Okay? Another thing to point out here, yeah, so if metadata has to contain sort of n pointers to other blocks, you also get a cubic dependency on n here in the multi-sender setting. Okay? Yeah, okay, so the main takeaway there is that it's completely different, right? So the factor n difference disappears. Okay, so now let's move on to state machine replication. To begin with, though, I'm going to compare single-sender and multi-sender protocols without the use of erasure coding. Okay, so perhaps not surprisingly, erasure coding changes everything. Okay. I'm going to take Sailfish as a representative example of a certified DAG protocol. You could consider other ones. You'll get some fairly similar picture. And importantly, yeah, we're going to consider both consistent broadcast and reliable broadcast as the underlying primitive for block propagation. Because, well, as you maybe not surprised from the previous slide, I guess a lot of the papers consider reliable broadcast as your underlying primitive. Turns out that's not a very efficient way to do things here, so you get much better results if you use consistent broadcast as your underlying primitive, although that gives some weaker guarantees. Okay, so here I won't show you the formulas, here are just some plots that give the sort of picture. Okay, so what can we see here? So the red one is Tendermint, the green one is Sailfish with consistent broadcast, and that's the one with the low latency here. The yellow one is Sailfish with reliable broadcast, okay, you can see it's not doing very well over there, and the purple one is Hot Stuff. Okay, so first of all, Sailfish with consistent broadcast is out-competing everybody else in this particular regime, basically because you have this factor n difference in where the latency bottleneck appears. Okay, we're not using erasure coding yet. Yeah. Okay, that's one thing to point out. Another thing to point out is that Tendermint is outperforming Hot Stuff, and that's true in all regimes here. Okay. Okay, and then lastly, let's look at what happens when we have erasure coding, and perhaps unsurprisingly, that things completely change. So here we have the red line is dispersed simplex. Here we're varying n on the x-axis, and here we're varying the incoming transaction rate on the x-axis. Okay. So basically, what you see here is the dispersed simplex, right, which is your single-sender protocol, but using erasure coding. It outcompetes Selfish with consistent broadcast for quite a wide regime, but the advantage of Selfish with consistent broadcast is it has a latency bottleneck, which is higher by a constant factor. Okay, so to summarize then, so for state-of-the-art SMR protocols, we end up with trade-offs. So if you compare single-sender protocols using pipelining, if you like, and erasure coding, such as dispersed simplex with DAG-based protocols, such as Selfish and Bullshock, so the former, right, the single-sender protocols have a lower latency for a wide range of throughputs. On the other hand, the benefit of the DAG-based protocols is that they have this higher latency bottleneck, right, by about to finish, don't worry, by a constant factor. On the other hand, the comparison with your standard single-sender protocols that aren't using erasure coding is a bit simpler, because there you really do have this factor n difference in the latency bottleneck. Okay, so I'll stop there. Thanks for listening.
Questions? I know it must be in the paper, so could you summarize how do you derive those latency formula? Did you use something like the good old queuing theory to do that?
The best thing to do, I'll be giving a talk at A16Z next week, and I'll go through an example of that one. So, yeah, it's not okay. It's obviously a bit more complicated than just counting the deltas like you did before, a number of rounds, but it's not that hard, right? I mean, there's a sort of you have to go through a bit of algebra and stuff, but it's yeah, okay.
A very simple question. The plots were all derived from the formula with specific values for the metadata size. And
yeah, that's right. Yeah, but I tried to make them sort of representative, right? So
Thanks for the talks. It's really interesting. So can you expand a little bit on what happens between best effort broadcast and reliable broadcast? Why is it so different? Because intuitively, it seems that the payload, you only send it at the beginning, and then you're only exchanging metadata. So why is it so different?
No, so the problem is if you're doing reliable broadcast and you're doing the multi-sender setting, there's the first round, say you're doing all simultaneously. There's the first round in which you're sending your own block, but then there's the second round in which you have to echo everybody else's blocks. Right? So that. No. You have to, if you're really going to do full reliable broadcast, then you have to echo the block, right, the actual content, to make sure that everybody has actually received the block. I mean, you can consider variance instead, something that's closer to consistent broadcast, if you like, and then you'll overcome this problem. Right? But if you're really just doing something like Bracker's broadcast, then you're echoing the block, and then you'll have this very inefficient round where everybody's echoing everybody else's blocks. Yeah.
Okay.
Any more questions? Cool. Let's thank Andy again. All right. What? Hello? Okay, perfect. So this concludes the day. We want to thank again all of our speakers. Thank you so much. We want to thank the sponsors, Pod and Babylon, and Berkeley RDI for providing the venue and the coffee, not in the morning, but in the afternoon. We want to thank Ilana for all the audio-video and miking up the speakers. And of course, the organizers, David, Camilla, and Srivatsan. And with that, enjoy the evening. See you all next year.